Alright, so continuing our lesson on kinetics. So last time we said you can examine the half-life to determine if your rate law is of the form rate equals K times concentration of reactant raised to the power n, right? So if it's zero order, what did we say the half-life does as the reaction progresses? It gets shorter. If n equals 1, what happens to the half-life as the reaction progresses? Stays constant. If n equals 2, what happens to the half-life as the reaction progresses? Gets longer. Let's look at this question right here. The rate law for this reaction is rate equals K times concentration of A, where A is your reactant. So if it takes half a second for the concentration of reactant A to drop from 0.1 to 0.05, that means getting it cut in half from 0.1 to 0.05. How long will it take for it to drop from 0.08 to 0.04? Is it, oops, lost my clicker. What happened to my clicker? Okay. Is it gonna be, oops, I don't have choices, huh? Okay, is it going to be less than 0.5 seconds? Is it going to be 0.5 seconds? Or is it going to be longer than 0.5 seconds? Okay. Somebody's battery's dying. Okay. What's the order of this reaction? First order, so it's going to be constant, right? N equals 1. So the order of reaction with respect to reactant A is 1. So it's going to take the same amount of time. It's going to be 0.5 seconds. Can we determine the rate constant here? Remember how to determine the rate constant? Rate constant is natural log of 2 divided by the half-life. So it's going to be 0.693 divided by, what's our half-life? 0.50 seconds. And what would that be? 0.693 divided by 0.5. It's 1.4. So 1.4 per second. Okay? Let's take a look at this one. Consider the data shown in the table here. If rate equals K times concentration of X, what's the concentration of X at T equals 0.2 seconds? Let's examine the numbers here. From 0.2 to 0.1, that's half, right? It gets cut in half. It took 0.1 seconds. So what's our half-life? When the concentration of X is 0.2, our half-life is 0.1 seconds. And according to this, rate equals K times concentration of X. So what's the order of this reaction? First order, right? So what would the concentration be at 0.2 seconds? How long did it take to go from 0.1 to 0.2 seconds? A tenth of a second to go from 0 to 0.1, a tenth of a second to go from 0 to 0.2. So what would the concentration be at that point? No. It will get cut in half. So what's half of 0.1? 0.005 at that point. At 0.3 seconds, another half-life would pass. What would the new concentration be? 0.0025. That's what first order means. It takes the same amount of time for it to get cut in half. It never goes to 0, right? 0, 0. Oh, yeah, I'm sorry. Yeah, it's 0.005. sorry, this is 0.1, so half of 0.1 is 0.05. Yeah. And then after that, it's going to be 0.025. Okay? Now, what if I ask you, what would it be at 10 seconds? Now, you don't want to just keep doing this, right? So what should we do? What you can do is you can use the equation for the first order rate law, right? What was the first order rate law? ln of A equals ln of A naught minus kt, right? So what is our A naught? So solve for ln of A. What's our A naught? What's our very first concentration here? 0.2. Okay, actually x. So we're gonna use letter x here. ln of x naught. Let me fix that. So ln of. Okay, let me do this over. I'm gonna say ln of x at time t is equal to ln of x naught minus kt, right? So you can say ln of x naught, so that's ln of 0.200, right, minus kt. What's our k? Remember, for first order rate law, what's our k? ln of 2 over the half-life, right? So 0.693 divided by our half-life, which is 0.10 seconds. So what's that? 6.93 per second. I'm just going to keep an extra digit there, although I only have 2 sig figs there because I'm going to use that for my calculation later. So it's 6.93 per second. So I'm going to say this is natural log of 0.200 minus 6.93 per second times how much 10 seconds later. So I'm going to put 10 seconds here. Let's make that 3 sig figs, 10.0 seconds. So seconds cancel out. So what would be ln of x at 10 seconds? What's ln of 0.2? Point 2, clear this, 0.2 natural log, it's 1.609, negative 1.609. By the way, when you're taking logs, okay, the rule of thumb is for sig figs is however many sig figs you have, when you take the log, that would be the number of decimal places you keep, okay? So minus, what's 6.93 minus times 10? That's 69.3, right? So what is negative 1.609 minus 69.3? $70.9, okay? So negative 70.9. That's ln of x at 10 seconds. So what's my x going to be? I take the inverse log. What's the inverse of ln? E to the negative 70.9, right? So this time you have, okay, clear that. So 70.9 negative inverse log. So inverse, that makes it e to the x. It's 1.62 times 10 to the negative 31. What do you notice about that? That is a very, very, very small number. Why? Well, every half a second gets cut in half. By the time you get to 10 seconds, it's going to be a very, very small number. Okay? but it's not going to be 0. Okay. Let's look at this one. It's just basically the same one as before, except that what would it be at time at 0.8 seconds? So what was our equation? ln of x equals ln of x naught minus kt, right? And we've already established this is the same problem as before, except that you're being asked for the concentration at 0.8 seconds. So ln of 0.200 minus 6.93 per second, but instead of 10 seconds, I'm just going to do 0.8 seconds. All right, so 0.8 seconds cancel out. That gives you how much? What was our ln of 0.2? It's negative 1.609. Minus, what's 6.93 times 0.8? 5.544. And that will be 5.544 plus 1.609. 7.153. Negative 7.153. So that's ln of x. How do I solve for x? E to the negative 7.153. So inverse. So make that negative. Inverse log. 7.825 times 10 to the negative 4. 7.83. Times 10 to the negative 4 moles per liter. Okay, so again, that's a small number. Not quite as small as at 10 seconds, because how many more times will this have to get cut in half? 0.2, 0.3, 0.4, 0.6, 0.7, 0.8. So how many more times? 1, 2, 3, 4, 5, 6 more times, right? So it's like saying you're multiplying your 0.1 by 1/2 6 times. So multiply by 1/2 raised to the power 6. That should give you the same answer. Okay, but you know, it's better to use this more generic formula right here to do the calculation, because not everything is a multiple of your half-life. So if you have like 0.85, then you won't be able to use a formula. You won't be able to reason it out like this. Okay. Here's an example of a first-order decay, first-order reaction. Okay. Carbon 14 is converted to it's radioactive. Okay. And it's constantly being produced in the atmosphere, and it converts to non-radioactive nitrogen 14 in about 5,600 years. Okay. The notion of this is practical application. This is for determining the age of fossils, using what is called radiocarbon dating. Radiocarbon refers to carbon 14. It's a radioactive atom. Okay. Radiocarbon dating is based on the assumption that the carbon 14 level in living organisms is constant. Okay, because you're constantly breathing in and out, and so your carbon 14 level would be constant. So that's a big assumption, though. And but once you die, okay, you stop breathing, right? So your carbon 14 in your body will start to decay. The level of your carbon 14, concentration of carbon 14 in your body will start to decay, and it's not being replenished anymore, because carbon 14 is generated in the atmosphere. So when you breathe, you constantly replenish it. So you maintain a steady state of carbon 14. Right? So once you die, once an organism dies, that carbon 14 starts to diminish, and it follows a first order rate law. Okay, so rate is proportional to the concentration of carbon-14. Now, the ratio of carbon-14 then in a fossil to the carbon-14 in a living organism can be used as a way of determining how old the fossil is. Okay? So let's say you had a fossil, you've compared the carbon-14 level in that fossil to a living organism and found that to be 0.25. How old is the fossil? Okay, so ln of carbon-14 in the fossil, right? You can say would be equal to ln of carbon-14 in the living minus kT. Okay, so ln of carbon-14 in the fossil over carbon-14 in the living. I'm not writing this well. Carbon-14 in the living is equal to negative kT. So what's the ratio we say of the fossil to the living? It's 0.25, right? Is equal to negative kT. What's our K? If it's first order, what's K? Half-life is 5,600 years. Okay, so that's your half-life for radiocarbon, 5,600 years. So K is ln of 2 over 5,600 years. So what's our K? .693 divided by 5,600. That's 1.24 times 10 to the negative 4, right? 1.24, is that correct? That's 1.2375, so 1.24 times 10 to the negative 4 per year, okay? So I can plug that in here for K, so I can solve for T, the age of my fossil. Is ln of the ratio, which is 0.25, divided by K, which is, what was it? 1.24 times 10 to the negative 4 per year. So that will give me the answer in years. What would that be? Clear that. So ln of 0.25 natural log divided by 1.24 times 10 to the negative 4, and that gives me and that's negative right here, so there's a negative, so there's a negative there. Negative, negative, that becomes a positive number. 11,180 years. Okay. Or 11,000. I'm just going to keep free sake fixed. So 11,200 years. Okay, so that's how old the fossil is, based on those assumptions. Now, you could actually have done this in your head because I gave you some nice round numbers. What's 0.25? 1/4. That's 1/2 of 1/2, right? So 5,600 years later, it will be cut to a half. Another 5,600 years, it would be half of a half. You'll have a quarter left. So that means this fossil has lived 2 half-lives of a carbon-14 atom. So 2 half-lives, 2 times 5,600 is, what's 2 times 5,600? 11,200. Okay, so you can work it out using this equation for the first order rate law, or you can just do it in your head, since like you know, in this particular case it's simple because it's a half of a half. So it's a, but if it's not a power of 1/2, the fraction remaining, then you're going to have to use the equation that I gave you here. Okay? Unless you can do that math in your head too. All right. The rate law for a reaction is rate equals K times the concentration of A squared. So that's second order. It takes half a second for the concentration to drop from 0.5 to 0.05. How long will it take to drop from 0.05 to 0.025? So is it going to be A, 0.5 seconds, B, less than 0.5 seconds, or C, longer than 0.5 seconds? Ready? This is second order now. Okay. Second order, the longer the reaction goes, the longer the half-life. Okay. So the lower the starting concentrations. It's going to take longer than half a second. How much longer? This one you should be able to do in your head. 0.5, starting at 0.1 versus starting at 0.05. Half the starting amount, so inverse proportion means it's going to take twice as long. So it's going to take 1 second. Okay? How do you work this out? Mathematically, you can say 0.5's your half-life times the starting concentration of A is a constant. It's a constant. So you can say then that 0.50 seconds times the starting concentration of 0.100 molar is equal to 0.050 molar times the half-life here would be x. Okay? And so that's going to be equal to what? One second, right? 0.1 times 0.5 is 0.05. So what would you multiply with 0.05 to get 0.05? X has to be a 1. Okay. What's the value for K? Remember, for second order, 1 over R equals 1 over R naught. Okay, in this case we can use A. 1 over A naught plus KT. Our K is equal to 1 over the starting concentration times the half-life, right? For second order. So what's our rate constant in this case? It's just 1 over starting concentration of A is how much? 0.1 moles per liter, and our half-life was, what was our half-life? Half a second, 0.50 seconds. So that gives me 0.1 times 0.1 times 0.05. 0.1 times 0.5 is 0.05. So 1 divided by 0.05 is 20. You're getting that? So it's going to be 20 per molarity per second. Okay? Now, what if I were to ask you, what would be the concentration of A, let's say, 5 seconds later? Then you just plug in your K here, you plug in the time here, you plug in 1 over A naught here, you plug in A naught, you can figure out 1 over A, and then just take the reciprocal of that. I think I have a problem similar to that right here. Okay. Is this the same question? Yeah, it's similar. This is from 0.08 to 0.04. What would you have to do here? Then you say 0.50 seconds times, starting from 0.1, right? Moles per liter is equal to X, the half-life, when you start from 0.080 moles per liter. So you divide both sides by 0.08, you can get your half-life right there. Let's look at this one. We got way too many questions for this part of the lesson, huh? This is second order. It took a tenth of a second to drop from 0.2 to 0.1. Okay? So, from 0.1 to 0.3, how long is that? That's 0.2 seconds. So, what would be my concentration by then? My second half-life would be twice as long, right? So that means 0.2 must be the half-life to go from there. So this is now going to be 0.05. Second order. First half-life is 0.1 second. The second half-life would be twice as long. So instead of 0.1, it's going to take 0.2 seconds for that. Okay? Another way of looking at this is as follows. You can say 0.200 times 0.1, okay, is equal to 0.1 times 0.2. Okay? Another way of looking at it. Half-life times initial concentration is a constant, second order. So you know that this is going to get cut in half because you're looking at a time that is twice the original half-life. What would be the concentration at 0.7 seconds? So this is, okay, this is second order. It takes 0.1 seconds for it to get cut in half. How much concentration would you have left? 0.7 seconds. At time equals 0.7 seconds. Okay, so this is second order. What do we know? K is equal to 1 over starting concentration of X times the half-life, right? So what's our K? 1 over 0.200 moles per liter. What's our half-life? How long did it take to go from 0.2 to 0.1? A tenth of a second. So what's 1 over 0.02? 1 divided by 0.02, 50, okay? So this is 50 per molarity per second. 2 sig figs, all right? So how do I solve for my concentration at t equals 0.7 seconds? What do I do there? I'm going to say 1 over x at time t is equal to 1 over x naught plus kt. This is the equation you use if n equals 2, second order, right? So what's 1 over x naught? X naught is our starting concentration. It's 0.2, right? So this is x at time 0, x naught. So 1 over 0.2 moles per liter plus our rate constant is 50 per molarity per second times our time. You're being asked for the concentration at 0.7 seconds, right? So seconds cancel out. Okay, and so this gives me how much? What's 1 over 0.2? 1 divided by 0.2 is 5. So So this is going to be 5.00 plus 50 times 0.7 is how much? 35. Okay. So what's 35 plus 5? 40. And what's the unit for this? This is per molarity, and that's per molarity, so that's per molarity. Okay? So 1 over x is 40 per molarity. So what is my x then? 1 over 40 per molarity, which would be 1 divided by 40, 0.025 molar. Okay? So it will be 0.025 molar at 0.7 seconds. 0.025. Moles per liter. Let's see if this makes sense. To get cut in half, it takes 0.1 seconds, right? If I want to cut this in half, what would I get next? 0.05, right? So it's going to take twice as long. So instead of adding 0.1, I'm going to add 0.2. It's going to be 0.3 seconds. At 0.3 seconds, it's going to be 0.05. If I cut it in half one more time, it's going to take twice as long now. So instead of adding another 0.2 seconds, I add another 0.4 seconds. So 0.1 plus 0.2 plus 0.4 will give me 0.7 seconds. See, the half-life gets longer as the reaction progresses if your reaction is second order. All right, so now let's talk about the method of isolation. So far, we've talked about rate laws that are very simple. It depends only on the concentration of one reactant. In general, the rate of a reaction will depend on the concentration of more than just one reactant. But because it's very easy to deal with rate laws that just involves one reactant, we do a trick here called the method of isolation. What you do in the method of isolation is you use excess reactants. All the reactants you're using, you use excess except for the one you want to study. Okay? So let's say you might see something like this in the lab. You have a reaction between a dye and sodium hydroxide. So your hydroxide ions will react with the dye. You might set up that experiment so that the concentration of the dye initially is very low, so like 0.0001. Okay? And then you have a large excess of your hydroxide. Let's say you use 1 molar solution of sodium hydroxide. Okay? Throughout the reaction, we say then that, okay, let's imagine that the reaction is completed. Okay? How much of, what would be your final concentration of hydroxide? Let's say you lost all of this dye. And let's say it's a 1-to-1 ratio for the stoichiometry. How much sodium hydroxide would you have lost? Same amount, right? So you would end up for the final sodium hydroxide solution, if the reaction were to go all the way, you'd have the starting amount minus the amount you've lost, which is 0.0001. What is 1.00 minus 0.0001? 1.00 minus 0.0001. Yeah, but using sig figs, it's still 1.00, right? It's like saying you took a drop out of the bucket. It's still a bucket left, right? So, in other words, throughout most of the reaction, the concentration of your hydroxide will be essentially constant. So you use a large excess of one of the reactants. In this case, your final sodium hydroxide will still be the same as your initial. Okay? Now let's examine the rate law. What happens to the rate law if that's the case? Rate equals some constant K, your rate constant, right? Times hydroxide raised to some power, correct? Times the concentration of the dye raised to the order of reaction with respect to the dye. But since throughout most of the reaction, the concentration of hydroxide essentially remains unchanged, you can lump this hydroxide concentration raised to the power x along with K into what we would call an apparent rate constant. So this will replace that with another constant. So the APP there means apparent. So that's your apparent rate constant. So that expression right there is apparently constant. So we replace that by K subscript APP. That means apparent rate constant. Okay, so now you've simplified your rate law. Now your rate law, according to this, will just depend on the concentration of the dye. So you run an experiment where you just monitor the concentration of the dye. And how do you determine what this Y is going to be? The order of reaction with respect to the dye. You plot concentration versus time. You plot natural log versus time. And you plot 1 over concentration versus time. Whichever one shows up linear, that will tell you what the order of the reaction is. Okay? So we say that the order of the reaction here is pseudo Y order. Okay, why is it pseudo Y order? Because it's not really just dependent on the concentration of the dye. It also depends on the overall order is actually X plus Y, right? But since we're setting it up so X doesn't matter because it's lumped into the constant, the apparent rate constant, you say you have a pseudo. So if Y it turns out to be 2, then you say your reaction is pseudo second order. If Y turns out to be 1, you say your reaction is pseudo first order. And like I said, you can analyze the data here using the techniques we learned earlier. And that's why we looked at that first. We looked at the simple cases first because this is a trick that we can use to simplify rate law, the things we look at in the lab, into simple rate laws that we talked about earlier. Okay? So let's take a look at this one. Let's say you run a reaction between X and Y and you form product Z. Let's say you carry out an experiment where first experiment, your concentration of X is 1 molar, your initial concentration of Y is 0.0001. And in the second trial, you double the concentration of X and your Y initial concentration is still 0.0001. So each individual trial, let's say trial 1 by itself, okay, will allow us to determine the reaction order with respect to reactant. Which reactant, A or X or Y? What would be the answer to that question? In fact, in other words, if you just ignore trial 2, okay, and just look at the data from trial 1, or ignore trial 1 and just look at the data from trial 2, can you determine the order of reaction with respect to one of these two reactions, and which one? It's called the method of isolation or flooding. Correct answer. Why? Okay. In the method of isolation, any given trial will allow you to determine the order of the reaction with respect to one of the reactants by flooding it with all the other reactants. This is excess. Throughout the reaction, your X is hardly going to change. What you'll actually be able to, the rate law for this one would be, okay, so rate for reaction 1, trial 1 would be equal to K times 1.0 raised to the power X times concentration of Y raised to the power, let's say Y. This whole thing right there would appear to be constant during that trial. That's an apparent constant. The trial will allow you to determine the order of the reaction with respect to the reactant that's present in small amount. Same thing with trial 2, except that in trial 2, what's your rate constant going to be? For your rate in trial 2, you'll also be able to determine the order of reaction with respect to Y. Your apparent rate constant is just going to be different. Okay, so you get a different apparent rate constant for the 2 runs. So that tells you then that these 2 runs will allow you to determine what? Allow you to determine X. Because the K apparent will be different. Okay? You're going to have different apparent rate constants for these 2 runs. So let's summarize what we do in the method of isolation. If R is your limiting reactant, okay, for any given run, the rate law is going to be equal, the rate is going to be equal to an apparent rate constant times the concentration of R raised to the power R. That you can determine, okay? And you can determine the apparent rate constant for that run. If S is your excess reactant, then your apparent rate constant for any given run is equal to the true K times the concentration of S raised to little s here, which is the order of reaction with respect to S. Okay? So you do at least 2 runs, different S values, same R. All right? So from that, you can determine your R for each run. And then what you do is you plug in the K apparent and the concentration of S for both runs, and that will allow you to determine the order of reaction with respect to S. You have 2 equations and 2 unknowns. So you have K app equals, so you have this one and this K and this S would be unknowns for each run. So if you do 2 of those runs, you'll have 2 equations and 2 unknowns. You can figure out the true K and the value of S. Right, so let's illustrate that. The apparent rate constant for the reactions of a dye with a hydroxide is shown below. Determine the true rate constant and the order of reaction with respect to hydroxide. So your apparent rate constant, okay, is just the true rate constant times the hydroxide raised to the power x. So for experiment 1, what's our apparent rate constant? Apparent rate constant is 2.00 per second equals the true K times, what's the hydroxide for experiment 1? 1.00 raised to the power x. For experiment number 2, what do we have? Our apparent rate constant is 8.00 per second. That's equal to the true rate constant. And what's our concentration of hydroxide for experiment 2? 2.00 raised to the power x. Do I have enough information to get the value for K and X? Yeah, I do. I got 2 equations and 2 unknowns. So how do I solve for K and X here? Okay, I got equation 1 and equation 2. A quick way is to divide equation 2 by equation 1. Okay, so what's 8 divided by 2? 4, right? Let me rewrite that. So I have 8.00 per second over 2.00 per second equals K times 2.00 to the X divided by K times 1.00 to the X. What happens here? What is 8 divided by 2? That's 4. K cancels out, right? What is 2 over 1? 2 to the x over 1 to the x. What is a to the x over b to the x? That's just a over b to the x, right? So this is going to be 2.00 over 1.00 raised to the power x. So that gives you 4.00 equals 2.00 raised to the power x. What is x? Should be able to do this in your head. 2 squared will give you 4, right? But if these are not nice numbers, not easy numbers to look at, then you can just say log of 4 is equal to x times log of 2. And you can solve for x. Divide both sides by log of 2. So x equals log of 4.00 over log of 2.00, and you should get to second order. Yeah. Uh-huh.
So you put a over b, a to the x over b to the x. You do the inverse for the example in the loop, and then you get to do the inverse.
I did not. It's a still on top, a still on top, b still at the bottom, b still at the bottom. Okay. All right. And you can actually sort of just eyeball this. You can say 1 to 2, you double your hydroxide, the apparent rate constant gets from 2 to 8. Quadrupled, right? You double one, the rate constant, the apparent rate constant gets quadrupled, so you can tell it's second order with respect to hydroxide. All right. Let's talk about determination of activation energy. As we've mentioned earlier, we said that in general, the higher the temperature, that when you do your reaction, the higher the rate constant, you get a higher rate constant and a faster rate. Why is that? Reactions occur because of collisions, right? So the higher the temperature, the faster the molecules or atoms are moving, the more often they collide. They have more energy to overcome what's called the energy of activation, the minimum energy you need for the reaction to occur. Okay? Arrhenius used what's called an empirical equation. That's just based on experimental observation. He was able to fit experimental data to this equation. K, the rate constant, is equal to some constant A times e to the negative e sub A. E sub A is called your energy of activation divided by RT. Okay, so that's how he was able, that's the equation he used to summarize experimental data that shows how the rate constant depends on temperature. Let's look at this equation. If you were to take the natural log of both sides, natural log of K equals natural log of A, okay, plus the natural log of this expression right here. What is the natural log of e to the negative EA over RT? In other words, what's the natural log of e to the x? It's just x, right? So the natural log of e to the negative EA over RT will just be this thing that's inside the e. So that's minus EA over R times 1 over T. So this is another way you can write your Arrhenius equation. So the Arrhenius equation relates the rate constant with temperature. So ln of K is equal to ln of some constant A minus energy of activation over R times 1 over T. Okay? Now, if you were to plot your experimental data, so you do a series of runs, everything identical for those experimental runs except for the temperature. Okay? So, and you're able to get the rate constant at each temperature. Okay, so you have a series of experiments. If I were to put this in my y-axis, natural log of K, and I put 1 over T on my x-axis, y equals mx plus b would be the equation for a straight line. What is negative EA over R? That's your slope. And ln of A is going to be your y-intercept. So if you were to make this plot, let me give this a little more room here. If I were to plot natural log of K versus 1 over T, I'm going to get a straight line with a slope equal to negative E sub A over R. In other words, if I want to determine my energy of activation, all I have to do is multiply my slope by R. What's the value of R? 8.314 joules per Kelvin per mole. Okay? So and what would be the y-intercept for this one? It's going to be natural log of that constant A, the pre-exponential factor. That depends on what the reaction is. Okay? So how do I get the slope of my line? I just need 2 points, right? I need to identify 2 points on the line to get my slope. First of all, let's see if this is consistent with our notion of rates being faster at higher temperatures. 1 over T, okay, but at very high temperature, what's my value of 1 over T? The bigger that denominator is, so this one right here, this side of my graph represents high temperature, okay? The smaller that denominator is, 1 divided by a smaller number would give you a bigger overall number. So the right side of this graph represents low temperature. So is that consistent then with what we expect? At high temperature, you have faster rates, okay, larger rate constants. At low temperature, you have lower rate constants, okay, slower reactions. So how do you determine the slope? Delta y over delta x, right? So delta y over delta x. What's delta y? ln of K2 minus ln of K1. Pick 2 points, 1 and 2, right? Divided by 1 over T2 minus 1 over T1. Okay? And what's that equal to? That's equal to negative E sub A over R. Okay? So that's one way you can determine your slope. From your experiment, you can calculate this. But what is ln of K2 minus ln of K1? That's what's another way we can write this. This is ln of K2 over K1. Remember? ln of x minus ln of y is ln of x over y. So divide that by 1 over T1, 1 over T2 minus 1 over T1. That will give you negative E sub A over R. So whatever this is my slope. You just multiply that by negative R. That will give you your energy of activation. Okay? Let's rearrange this equation in something you might see in your textbook. You'll see this written as ln of K2 over K1 equals negative E sub A over R. I'm going to move this thing right here over to the right side. So that's going to be 1 over T2 minus 1 over T1. So this is another form of the Arrhenius equation. Okay? So if you know K at T2 and K at T1, you can solve for the energy of activation. It's just negative R times the slope. Okay, so that's how you determine your energy of activation. Here it is. Slope is ln of K2 minus ln of K1 divided by 1 over T2 minus 1 over T1. All right? And ln of K2 minus ln of K1 is just ln of K2 minus K1. What's the unit for your slope? Let's look at our slope. What's the unit for the numerator here? ln of K2 over K1. The unit of K2 and K1 will cancel out, right? So your numerator is unitless. What's the unit for the denominator? 1 over, what's the temperature unit? Kelvin. Make sure you plug in numbers in Kelvin. So this is 1 over Kelvin. So the unit for your slope is Kelvin. Okay? This is the temperature unit. So, like I said, E sub A, energy of activation, is just going to be negative R times your slope. And this is in Kelvin. Okay? And your R is joules per Kelvin per mole. So if you multiply the two, your energy of activation would be in joules per mole. That would be the unit for your energy of activation. Let's take a look at this example right here. ln of K versus 1 over T. Look, okay? Estimate the rate constant at 25 degrees and 95 degrees. What would you have to do? What's 25 degrees? Uh, 298 Kelvin, right? So 1 divided by 1 divided by 298 Kelvin. 298 Kelvin is 0.003356. That's 1 over 298. Where is that on my graph? It's 0.03033. So it's down here, somewhere down here. Okay? And so that would be my ln of K there. And then K will just be E to the ln of K. At 95 degrees, where would I be? What's 95? 1 over 368 would be 1. 1 divided by 368, 0.00271. 1 over 368. 0.00271 is right here. That's at 95 degrees. So this is the data at 95 degrees. Down here is the data at 25 degrees. Okay? So here's a graph of ln of k versus 1 over t. You have the slope and the intercept. What would be the energy of activation for this? Minus r times the slope, right? So what's our r? 8.314 joules per Kelvin per mole. And what's our slope? Negative 6014. That should be in Kelvin. So that gives us 8.314 times 6014, 50,000. So 50,000 joules per mole. That's about 50 kilojoules per mole. That's typical for most reactions, around that. And with that energy of activation, the rule of thumb is to double the rate of a reaction, you have to raise your temperature by 10 degrees. So at 25 degrees versus 35 degrees, you usually see a doubling of the rate of reaction. And that corresponds to an energy of activation somewhere around 50 kilojoules per mole. Okay? And in fact, if you did that, you can do that calculation right here. And we're out of time, so we'll see about doing that next time.